Okay, so let's try an example of a line integral. This is not, however, a scalar line integral. Clues for telling the difference between line integrals and scalar line integrals are basically what kind of a thing are you looking at, right? Like a scalar line integral, what do you need?
Scalars.
Yeah, you need a scalar function, right? Here you have a vector.
Function.
Yeah, this is a vector valued function, right? This thing's a vector field. You guys with me on that?
Yeah.
So this is not going to be a scalar line integral. This is going to be a kind of a vector line integral, right? A work line integral. So when they ask me to calculate the work done by f of x and y is y comma minus x over the right-hand circle of S1 from 0, 1. First, I think I need to sort out what the hell path are they talking about?
Isn't this the?
Yeah, so S1's the unit circle. The right-hand side is the which side? The right one. Okay, cool. So my path that I'm talking about is, and it's from 0, 1, right? So it's going from the top to the bottom on the right-hand side. Is all cool with that?
I thought that function rotated counterclockwise.
Ah,
This is y
now
negative.
this vector field might actually go the other way. You guys see that? Like if I think about this vector field at 0, 1, right? So let me just, what's f of 0, 1? Like what's the situation starting at? This is, let's see, the y is 1, comma,
This is 0
0. So this is pointing
to the right.
to the right. So at the, sorry, and I put that in black and I really shouldn't. Because my curve is in black, right? And the vector field is kind of chilling in the background here. Should maybe get a different color. Wish I had a marker that worked.
Oh well.
But if it was 1 comma 0.
Hey, wake up.
Okay, well, it doesn't really matter. It's all being polynomials.
What?
1 comma 0 would be on the x-axis, right?
So remember, this is based at the point 0, 1, right? The vector result is 1, 0. So at the point 1, 0, you have a flow that looks like 1 over 0 up. Now, where else, like someplace else along this, you might have different flows. You guys cool with this? Like for instance, up here at 1, 1, what's this thing? 1, negative 1, right? So we're going right 1, down 1, so I get a vector that's square root of 2 long pointed that way. Does that look in general like this thing's going to help me or hurt me along this curve? Looks like it's probably going to help. So I should hopefully get a positive answer out of this thing. You guys down with that? Why am I thinking I should get a positive answer? How do you figure out the work done? Like,
Oh.
what were we doing
dotted.
yesterday?
Dots.
We were dotting
The flow.
the flow with the,
actual formula or whatever.
yeah, I was dotting the tangent line with the vector field, right?
Yeah.
But now I want to go from here to there, right? So to go from here to there, crap, I think I need to chunk this thing up and maybe make an integral or something, right? So what are the things I should be adding up here?
Slices of the line.
I should be adding up little bits of line, right? Times little bits of vector field, right? So I should be doing like f of r of t star, right?
It's not. Oh, it's not.
So that's me thinking out here, right? There's some t star. That's this guy. So that's happening at t equals t star. And there's a blue bit there, right, which might look like this. So that's this dude. And what should I be dotting that with?
The tangent of the parameterized curve.
I should be dotting that with r prime of t, right, which is going to look like this. And what's that dot product going to tell me?
How much they agree.
It's going to tell me how much they agree, right? And then, ooh,
dt.
oh, I need a t star there, right? You guys see that? Kind of with me? And then I think I need a delta t in here. Yeah, this looks a lot like a scalar line integral, right? Except that normally this would be the height of your fence and you mag this thing. Right? A very similar reason applies. Like you can chase all this down and you'll get this thing dotted with this thing and times the delta t if you chase this all the way out. It's basically the same thing we did with scalar line.
When we put this in the limit,
Uh-huh.
what happens to the magnitude of r prime of t? Does it go to 0?
No, that just becomes the magnitude of the derivative at a point. So on this guy, right, I'm going to send this delta t to 0. I don't have a magnitude here, so I'm not worried about it, right? But in the magnitude case, it's fine. The mag just stays. Let's cool with this? So as I take a limit going to 0, I should get, what? An integral of f of r of t
All t's.
dotted with
r prime of t
r prime of t
dt.
dt.
Are you sending to 0, delta t?
Yeah, I'm sending the number of slices to infinity or sending the delta t's to 0.
What is the bounds in this?
Good, perfect. What are the bounds?
Is it 0 to 1 or is it 0 to pi?
Okay, so the bounds are going to depend on how you parameterize your curve. Okay, so the bounds are t sub beginning to t sub end, and those are going to depend on how you draw that curve. You guys see this? Because there's more than one way to skin this particular curve, right? Like you can come up with a couple parameterizations that'll give you the same curve, but what those t's are depend on how you parameterize that thing. That's going to change your derivative, right? You guys see that? So when I change that r of t, it's going to change this piece, it's going to change the derivative, and it's going to change the bounds. So I would recommend you start with coming up with that thing first and then cram that in here. Cool? Okay, so on this guy, I think I need to come up with what? What's your first thing?
What is the
It seems like everything's based on that r of t thing, right?
Yep.
So I need to take this picture about the right-hand side of the unit circle and turn it into some r of t, right? Okay? First guess.
So we can do r prime of t equals f of xy, correct?
Equals f of x, y.
The theme that we've been using previously, that's
F.
Oh,
r prime.
you don't know this is a flow line.
Oh, okay.
Do you guys see that? If it's a flow line, the work done is maximized, right?
Oh.
But I don't know this thing's a flow line.
If it was a flow line, isn't r prime of t just equal to f of r of t, and that would be like squaring r prime of t?
Uh-huh. Yeah, you'll get the maximum magnitude out of this thing. You see that? Mumble that again louder, Brandon.
Would it actually be rather the idea to do the r cosine, r sine, or y?
Okay, first guess. Slap a cosine t sine t in here, right? Because, yeah, because polar, because circle, right? There's a circle. Try cosine and sine. That should be your go-to. Does it work?
No.
No.
Because,
Why?
At t equals 0 cosine, it should be at 1, 0, not 0, 1.
Okay, so don't get hung up on where the t's are.
Okay.
But do get hung up on the, yeah, get hung up on the direction of this thing. Because if you go the wrong way, you'll get the opposite sign, right? You guys see why?
Mhm.
So I need to go that way, right? I need to go clockwise around this thing. And my usual parameterization goes counterclockwise. So to get it to run the other direction, what do I need to do?
Make the negative sign.
Yeah, flip the y coordinate. That'll work. That's really flipping time over.
Could you also just make cosine t negative and leave sine t positive?
You could try. So if you make this bit negative and that bit positive, things will be confusing.
Yeah.
You could figure it out. It'll work, I think.
You're stuck.
I would do it this way because the way I think about this is I would say, okay, time normally runs this way. I want time to run backwards. So I'm going to slap a minus t in here. And then cosine's even, so cosine of minus t and cosine of t are the same thing.
Yep.
And sine's odd, so sine of minus t is the same thing as minus sine of t. Great.
Can you explain why you did y is equal to cosine t instead of sine t first?
Why? Oh, I'm not doing anything with that vector field.
Oh, okay.
I'm just doing the circle.
Just doing it.
We'll use the vector field here in a second. You guys all good with this? Okay, and there, like I said, there's more than one way to skin this thing. You could adjust the period. It would just make for confusion. I would go for the standard, easiest parameterization you can find. Okay, now where do your times run to get the right-hand side of the unit circle?
Or 3.
Or three.
Is it 0?
No, because that would be that
five?
way.
Yeah, you're right.
You have to go this way.
Yeah, so I made time run
Oh.
backwards, right?
No, it's
Let me just check.
it's negative pi over 2 to pi over 2.
It should be negative pi over 2 to pi over 2. If you do pi over 2 to negative pi over 2, you want, in fact, the usual parameterization. That's totally an option.
Okay.
You guys see that? Like you could do the usual parameterization and then just put your limits backwards. That would totally work. So I'm going to do it this way, and I'm going to say my t's range from minus pi over 2 to pi over 2.
I was just about to say, is it supposed to be brackets or?
Does it matter?
I think
No,
you
it's
do
just the area over a point, right? So it's not going to matter. But sure, let's toss it in there just for kicks. Okay, so I would like to make sure that this works, right? So I should plug in minus pi over 2 first. Just in here, just to make sure I've got,
Yep.
make sure I'm getting 0, 1 out, right?
Which you do.
So if I plug in minus pi over 2, I
Cosine.
think I get
is
0 out of cosine
And
and,
negative 1 out of sine, and a negative sine turns it into a positive one.
yeah? Okay, cool. And if you plug pi over 2 in, do you get this end?
Yep, 0 and then a negative 1.
Yep. And most importantly, make sure you've got the right-hand side, not the left-hand side. So what else do you need to plug in?
0, that number in between.
So you plug 0 in, so you get
1.
1, 0. Cool. Right-hand side, probably. Right, checking 3 points isn't actually enough, but I know this is a circle. I know I went with the usual kind of, I'm running time at speed 1, so I'm not worried that I've wrapped this thing a couple of times. You guys see that? Like if you put a 4 in here, you might be like, oh, how many times did it go around? I have no idea. Like, you could conceivably cover this a time and a half or 3 times or some weird thing, right? So don't mess with the period if you can avoid it.
Okay.
Okay, now how do I set this business up? I need to get out my integral, right? Okay. So where's your t beginning? Negative pi over 2. Where's your t end? Pi over 2. Okay. I'm going to ignore that part for right now.
Did we?
I'm going to put a dt over here.
Did we just?
No, hang on.
For the negative pi over 2, didn't we just say we could flip?
You could if you use the
Yeah.
usual parameterization.
Right.
I switched time backwards, so now my
I
my
just wanna make
t's
sure.
run the usual. Got it.
Sorry.
I flipped time over to make my parameterizations, and so my times run the usual way.
Okay.
You could, of course, use the usual parameterizations and just actually run time backwards.
Okay.
That would do the same thing.
I just wanted to make sure. Okay. Thank you.
Yeah, no, that's a very good question. So, what two vectors should you be dot producting?
Function of RT and R prime of T, we said?
Okay. Okay, now this is going to be a little confuzzling because these are going to look really similar.
So then you plug the RT into your F.
Okay, so you need to take your R of t and plug it into f. Right? So I'm doing f applied to cosine t comma minus sine t. Right?
Which is
So you should get
Oh.
Sine t,
Or-
no.
negative sine t.
Negative sine t.
Right? That thing in the y slot goes in the x slot,
Negative cosine.
comma, negative cosine t. Is all good with that? Okay. Now I also need to calculate r prime of t.
negative 17.
Which is negative sine t, comma,
Negative.
cosine t.
Or, yeah,
Right?
wait,
Those are the same. What the f? What's up here?
wait, isn't it supposed to be negative cosine t?
It's negative cosine t. Now they're the same. What the f?
Yeah.
I got ahead of myself. I was so excited that they were the same. So what the f?
Oh, it's a flow line.
It's a flow line. Cool. We're going to see how much help this thing can give us, right?
100%.
Yeah, so this vector field, right, is going to do as much work as it's capable of along this particular arc. You guys cool with that? Okay, so you should be dotting minus sine t minus cos t with minus sine t cos t, or minus cos t. Cool? And so, out of this jazz, whoa, what category of thing is that?
I mean, the dotting edge should be a scalar.
This guy should be a scalar what?
A scalar function?
Yeah, that's a scalar function of t, right? And then you're integrating it over the t's. So out of this, I should get a
Scalar.
number, right? A scalar. That's good. If you've still got x's and y's kicking around in this thing, you have missed a substitution someplace along the line. This object should be a scalar. You guys cool with that? I find that the thing that most students can do, that they'll get the r, and then they get r prime, fine, they toss it in there, but this guy still has x's and y's in it, because they forget to make that substitution, and then they get some scalar function of t, x, and y, right? And then everything turns into a giant disaster. So careful, careful, get it all to t's. So what do you get here? You get the integral from minus pi over 2, pi over 2.
Don't we get sine squared of t plus cosine squared of t, which is 1?
Perfect. So you get 1 dt. That's good. That should be a constant if you're looking at flow. No, never mind. I lied. It won't necessarily be constant. And so you get out of this pi.
What does it mean?
Which is the length of this.
Which happens to be the length of this circle, right? You guys
So
see that?
it's
That's
work
the
is equal-
length of this half circle.
The work is equal to the magnitude of the.
So the work here happened to be equal to the arc length, right? Why is that? That's because the flow lines along that are all unit vectors.
And it was in the circle.
And because this is a unit, and because this is a, so these guys are all unit vectors, and this is a flow line. Right, so at each point, it's helping one unit worth, and it's going pi units, so this thing's doing a total of pi units worth of work to help you out. You guys see that? Cool?
Yep.
Questions?
Does that,
So as that pi number goes to 0, theoretically, like that's more of how it's like helping you less and less and less till it's not helping you at all, and then as it becomes negative, it's what's hurting you.
Yeah, so if the answer, right, if I think about my answers here as varying, right, the answer you get out of the problem, if it's positive, this thing was helping you move along this kind of path, right? In other words, this would tend to happen on its own, right? If it was 0, it's just not helping, it's not hurting you, it's just not helpful, not hindering. But if it's negative, then it's actively hindering you, right? You're going to have to put some work into this thing to get that to happen.
it's going up, down
You
escalator.
guys see this? You can use this as a really coarse estimator of whether you need to put energy into a system or not, right? It does not, however, actually mean that you get away without putting energy in the system, because if you think about being a little man, right, who's going to go for a walk in a gravitational field, right? So here's your F vector, right? It's pointing down. What is the integral over this path going to be? So if you want to go from here to here, what's the result of that line integral going to be?
Positive?
Yeah, that's going to give you a positive answer, right? Does that mean you don't have to put any work into this thing?
No.
The net work.
Yeah, it means that if you have an electric car with perfect brake reclaiming, right, that you can go to the top of the hill discharging the battery and then charge it back up on the way down, and you'll get some capacity out of that. You guys see that? This also assumes that you're not going home. Right? Because if you go from here to there and then come back,
Neutral, right? Or
yeah, you'll get 0 work, right? That doesn't mean it's no work for you, right? Because you're going to lose something to friction. Okay, see that? Okay, so this is in, of course, an ideal frictionless world, right? These flows also tend to assume that that field doesn't have any friction. You guys remember we were talking about wading across rivers the other day?
Yeah.
Right? And the issue with wading directly across a river, even though that river is doing no work on you, it feels like it's hindering you, but that's just friction. Guys all good with that?
The fact that we're not pulling onto a metal pole, so
Yeah, exactly. Even if you are holding onto a metal pole, your arm's going to get tired.
yeah.
Okay, cool. Questions, concerns, Steels? Okay.